All right, today we'll be talking about gas properties and the kinetic molecular theory. So first we're going to do this FET. It's made by some CU professors. Hats off to them, thank you. And go through and see visually what it looks like to have gas in a container. So here's my container here. I'm going to pump in some gas. So right now you can take a look. Our temperature is 0 Kelvin, or not existent. I guess would be more appropriate. All right, so we pumped in some gas. We can see our gas molecules are represented by these round molecules flying around. As you'd expect for gas, it fills its container and it's bouncing around throughout the container, right? Okay, so what we're gonna do is we're gonna maintain our temperature. Our temperature is 300 Kelvin, and we're gonna maintain the amount of molecules that we have in here. So if we increase the volume, what do you think will change? Take a look. We're going to keep our temperature at 300 Kelvin. Take a look at our pressure. It's about 6 atmospheres. I increase my volume. What happened to my pressure? Looking over here at my pressure gauge, it's now bouncing around 4 atmospheres, whereas before it was 6. If I were to now decrease that volume, my pressure jumped up to about 11. If you think about to 12, bounces around. If you think about why that is, remember when these particles hit the wall, the more frequently they hit the wall of its container, the more pressure that wall will feel on it. Okay, so it's directly related there. And when you decrease the volume, the particles don't have as much space to move around, so they'll hit the walls more frequently, and the wall will feel the pressure that much more. Okay, alrighty, let's reset. Let's pump some more gas back in. So there goes my particles. Alrighty, so we are going to set our pressure constant. So let's set our pressure constant. So it's going to be set at 5.8 atmospheres. Now, if we were to increase the temperature, well, let's take a look. Let's increase the temperature. Whoa! So I'm keeping my pressure fairly constant. I increased my temperature from 300 Kelvin to 250 Kelvin, and I had to increase my volume in order to maintain pressure. Okay, I have to keep my pressure the same. Here we go. Now let's cool it. What happens now? Maintaining the same pressure, when we cool it, the volume has to decrease. Now, the reasoning, if you think about that, let's just look at visually what's happening here. When I increase the temperature, and I'm leaving pressure to increase or to change as it will, okay, as I increase, the temperature is going up. There's a direct correlation between the speed of the particles and the temperature. Remember when I was talking at the very beginning of the year about Kelvin, how it is a direct measure of the kinetic energy of the molecules? This is a visual representation of that. The faster they're moving, the more kinetic energy they have, which means they're a higher temperature. Okay, so if they're moving around faster, they're hitting the walls a lot more frequently, right? And so the pressure increases. In order for that pressure to stay the same, the volume would have to increase so it doesn't collide with the walls quite as frequently if you increase the temperature. If you think about it, this is kind of how hot air balloons are controlled, right? You increase the heat if you want to go up in elevation, and you turn off the heat and let it kind of cool if you want to start dropping down a little bit. Hot air balloons are just a bunch of air in there, right? And it has unlike this is a rigid container. A balloon is not. It can continue to expand. And by continuing to expand when it gets hot, it will decrease its density, allowing it to rise. Right? So that's how the hot air balloon works. Anyway, all right, let's reset and let's look at another experiment. So if we were to this time keep the volume and number of particles the same. So again, let's put the particles in. Alrighty, we are going to keep the volume constant, so I can't change it. That handle went away. All right, now what do you think will happen if I increase the heat? So take a look, we've got 300 Kelvin and the pressure is bouncing around 5.56, somewhere in there, atmospheres. If we increase my heat, we're going to see those particles start to move around faster because their kinetic energy is increased. Remember, a direct correlation between kinetic energy and, or the speed of the molecules, right? Kinetic energy and the temperature. Because they're moving around faster and hitting the walls more frequently, our pressure increased. Now, similarly, if I now cool it, you can see our pressure gauge is starting to decrease because our particles are slowing down, hitting the walls less frequently, so the pressure decreases. All right, let's look at one more thing here, and then we'll go into kinetic molecular theory here in a sec. All right, so I've got my gases back in there. So the volume stays the same, right? So I'm going to set that constant again. Now, what do you think will happen if I pump in more molecules? So we can see right now with this many molecules, I have a temperature of 300 Kelvin, and my pressure again is around 5.5 to 6, fluctuating there. If I pump more particles in there, we'll do 2 good pumps. Okay, let's take a look at our pressure. What's happening to our pressure? It's increasing, right? More particles in there mean it's going to collide with the walls more frequently, increasing the pressure on the walls. So the more particles I have in there, the more pressure. And I'm pretty sure if I do a whole bunch, let's see what happens. I'm just going to pump in a whole bunch of particles. Oh my gosh, look at that pressure go up and up and up and up and up. Similarly, if I took some of those molecules out, which the simulation won't let me do terribly well at the moment, it will go down. But I'm pretty sure if I pump enough particles in here, let's pump some other particles in here. Pressure continues to rise. Yeah, there it goes. It has a release. So look at that. We have a bunch of the particles are leaving and our pressure now is decreasing. It exploded out of there. All right. So those are the relationships I wanted you to see with this FET. Let's take a look at the postulate of kinetic molecular theory of gases. So based on what you saw, hopefully this is going to make more sense. So gases are made of tiny particles. Okay, and those are visualized with those balls, and they're way smaller than what that visual showed, but we needed to be able to see them for the visual, right? Alrighty, so you can assume the size of the particles to be negligible or 0. The size of a gas particle is so small that we assume it to be essentially 0. Thirdly, gas particles are constantly moving and colliding with the walls, causing pressure to be exerted on the wall. So that's what we were talking about. Remember, if they hit the wall more frequently, the wall feels a higher pressure. If they hit the wall less frequently, it feels less pressure. All right, fourth one, gas particles do not repel or attract each other. Okay, so this is the ideal gas law, right? So we're assuming that they're going to hit one another and kind of ricochet off like we saw in the visual. None of them were attracted to one another, nor did they repel one another, which would change the way that those gas particles interact with each other. Now, it is possible that you might see that in real life, but we assume ideal gas law, so that way it makes life so much easier for calculations, and it gets us really, really close to what we actually observe. All right, and then the fifth postulate is that the average kinetic energy of gas particles is directly proportional to the Kelvin temperature of the gas. Remember, I said that Kelvin is a direct measurement of the kinetic energy, and that's the speed at which those particles are moving around. As we saw when we heated it up, they sped up. When we cooled it down, they slowed down. Okay, that's what I've got for you today.